Do you ever struggle to find an answer to your question by looking through articles on the internet? You're not alone. As of today, Wikipedia comprises more than 55 million articles, attracting 1.7 billion unique visitors per month, and that's just a small fraction of textual data out there. As a part of our work this semester, we've developed an application that is capable of carrying out two tasks in the realm of automated information retrieval. Firstly, given a document, for example the text of a document from Wikipedia, to generate a set of questions relevant to that document. And secondly, given a text document and a set of questions, the system must return an answer to each question. The text file is passed through the preprocessor, which cleans the text and conducts tasks like POS tagging, semantic role labeling, and named entity recognition. Depending on the case, the preprocessed text is fed to the question generator or the question answerer, which work along with the text ranker to produce the necessary output, which is passed through the post processor before being displayed on the screen. This flowchart represents the question generation component. Everything centers around questions from sentence, which takes a single sentence and generates all the possible questions we can get from that sentence. The model splits the sentence into four main categories: subject, verb, auxiliary verb, and the rest of the sentence, which are replaced and moved around to generate good questions. The question generator follows a highly iterative process, generating questions and performing specific tasks, such as inflecting the root verb for certain questions. The preprocessing tasks were extremely useful for increasing the conciseness of the output. For ranking, the strategy of finding the average length of all questions and returning the questions closest to this average worked out better than directly ranking based on readability. Here's an instance of the dependency trees used for syntax visualization and debugging. We promote diversity in terms of question type and introduce a random sampler to make the output non-deterministic. The answer generation algorithm relies on the answer function, which is wrapped up using text preprocessing, candidate selection, and actual answer extraction. These tasks are primarily conducted using NLTK libraries and BERT models which have been fine-tuned to answer questions. Once we have the answer, it is subjected to post-processing. The illustrated workflow of the answer generator depicts that the most important steps are selecting the candidates and extracting the actual answer from candidates. We tried using word vector distance to ensure our selection can deal with synonyms and antonyms, but soon discovered that using cosine similarity to select answer candidates was a better option. Backed by a good selection method and a fine-tuned BERT model, the system is able to find the right answer. Some of the post-processing involves removing hanging conjugations and ensuring proper punctuation and formatting. Here are some of the key insights and observations drawn from our work on the system. Semantic role labeling played a crucial role in generating factual and binary question types. We decided against using the synonym generation and mapping module since we noticed that cosine similarity accounted for out of vocabulary words, and this will also drastically reduce our search space and runtime. We were able to predict the confidence of answers generated by BERT by using the return gradients. And finally, pre-processing and post-processing the text played a crucial role in improving model performance. We conducted extensive manual testing to evaluate the system and ran ablation tests to determine the efficiency of certain components. To ensure fluency and reasonable output, we ran checks to assess grammaticality and readability. To quantify the evaluation of our system, we ran tests on a manually annotated gold standard consisting of approximately 120 question-answer pairs drawn from different documents. We used Levenshtein distance and accuracy to judge the performance of our system. The best results come from using the system consisting of a cosine similarity filter to select the top 15 answer candidates, followed by the fine-tuned BERT model initially trained on the squad dataset. The displayed scores don't consider unanswered questions, which are roughly 20% of the input. Some of the auxiliary experiments that lend support to our system include a random forest model to classify questions by type, assessing text readability using the library textstat, and calculating word movers distance. Using Levenshtein scores with a threshold to determine answer accuracy proved effective in practice, as did using auto-generated as well as handwritten questions for BERT fine-tuning and evaluation. Ruling out answers with low confidence scores was another useful element. Here we have some sample output of our question generator. The question generator has four distinct methods for generating questions. Most of the questions shown here are generated using the first method, subject replacement, which is the simplest, most common, and most likely to produce reasonable output and is performed by first identifying a sentence with a simple SRL structure, usually argument, verb, argument, along with some modifier arguments. The argument which appears first in the sentence is identified as the element to be replaced by the question word. We use named entity recognition to determine which question word, such as what or who, to replace the subject with, and leave the rest of the sentence order unchanged. The latter three methods are slightly riskier but can produce more interesting questions. First, there are questions generated from prepositions. A fact such as Archduke Ferdinand was killed before the First World War can be mapped to before what was Archduke Ferdinand killed. This is done using the dependency tree, by which the preposition and object of the preposition are identified. Another method is to ask about the modifiers from SRL in which case before the first verb will be marked as a time modifier, so we remove it, move the auxiliary verb, and create when was Archduke Ferdinand killed. The last is the most complex, which is used in cases when the subject is being acted on by another noun phrase in the sentence, and is achieved using the specific labels in SRL. As for answering questions, the answer generation model can detect the question type correctly and integrates the answer based on this identified type of question while post-processing. Based on our inspection, the answer module is capable of successfully extracting factual information such as time, location, and name, and usually generates correct answers if it can find the right candidates. Binary questions are generally answered accurately if the question is derived from a sequence of sentences found in the text. Some tricky situations arise when the question is based on an inference drawn from a group of sentences which is not easily interpreted from the text. For such situations, and for questions which are deemed unrelated to the provided input document, we print a custom message when the system is unable to answer the question. Most of the challenges faced were in terms of identifying bad questions and ranking them. In terms of answering, it was hard to deal with twisted binary questions and answer vague and generic questions. Our future work will aim to address these challenges.